Hi, my name's Emma Watts and I'm a third year PhD student at the University of Southampton. Today I'm going to talk to you about the evolution of three volcanoes, Alu-Dalafilla and Borale, which are all situated in Afar, Ethiopia. The aims of this study were to create an updated, high-resolution map that was accompanied by a relative chronology of the volcanic products. As well as this, we also wanted to understand how the geochemistry of the volcanoes varied over their lifetime. The study I'm presenting today has been recently published in JVGR, so have a read if you like what you see. Afar is in East Ethiopia. It is of geological interest due to the on-land rifting of three rifts meeting in the area around here. The Gulf of Aden rift began rifting about 35 million years ago. This was then followed by the Red Sea rift 28 million years ago, and then finally the main Ethiopian rift approximately 18 million years ago. As a result, the crustal thickness around each rift varies, with the thinnest crust being in the Gulf of Aden and Red Sea, where rifting has been occurring the longest. To the west and the south of Afar, we can see areas of high elevation. This is known as the Ethiopian Plateau, which consists of continental flood basalts thought to peak at about 30 million years ago. Volcanism has been occurring in Afar since 45 million years ago, with the history of the region shown in the diagram here. In this study, we're interested in the Erte volcanic segment, which is an axial volcanic range with activity mostly being less than 600,000 years old. Here we focus on three volcanoes in the north of the Erte volcanic segment. These volcanoes are Alu, Dalafilla and Borale. While these are active volcanoes, very little work has actually been done on these since the original field campaign that went out in the 1970s. They created the map shown here on our right. Our aim was to improve this map and create a chronology of the activity. So, now on to our map. We created a geological map of lava flows using remote sensing. The satellite data was a mixture of Landsat 8, ASTER and other satellite images. Unfortunately, no fieldwork was done in the area due to political instability at the time. The map here shows the outline of over 92 lava flows, which were identified. This did not include Phase A, shown in dark blue, which is a base layer of lava found across the region. The locations and the names of the samples analysed are shown on the map using the white symbols. Once the lava flows were mapped, we looked at the overlap relationships in order to create a relative chronology. When this wasn't possible, we used other indicators such as weathering extent to estimate the relative timings. Unfortunately, argon dating of the lavas was not possible. From the overlap relationships, we identified four main phases of activity. Lava flows were grouped together by their location and where the characteristics of the flows were similar in nature. When doing this, we found that the area covered by the lava flows appeared to decrease over time. We are now going to briefly go over the characteristics of each stage of volcanism. Stage 1 consists of four phases. The products were characterised as being blanket-like and highly weathered, with no flow characteristics remaining. Barbary attributed the increased weathering to them being submarine at some point in time. However, no petrological evidence of this was seen in the study. The first phase, known as A, is the most widespread, occurring across the whole area. Phase B can be found on the eastern side and is sourced from 2 points. Phase C forms multiple flows and from a mixture of cones and fissures. And finally, Phase D is mostly around Borale and appears to be an old shield volcano situated to the west of the current volcanic centre. Stage 2 consists of three phases of activity which moved in a clockwise direction around Alu from west all the way round to the northeast. The products were mainly sourced from fissures situated around the base of the Alu dome. All flows were pahoe-hoe in nature. The total area covered was a minimum of 220 square kilometres. Each phase of the activity produced similar amounts of lava, ranging from 72 to 80 million cubic metres. All volumes were estimated by a simple calculation of area multiplied by average thickness of the lava flow. Stage 3 saw a change in style. Almost all activity in this stage was from the volcanic centres themselves, except for Phase H. Activity occurred from all three volcanic centres. The first activity of Stage 3 referred to as phase H, produced thick RR flows and had the greatest volume, approximately 347 million cubic meters. This activity was sourced from the western side of the Alu Dome. Following this, activity occurred at Borale Volcanic Center, which is known as phase I. These lava flows were much thinner, on average about 1.5 meters, and the volume was around a third of that produced in phase H. Some pumiceous products can be seen to the southeast of Borale, shown here. Finally, activity occurred at Dalafilla's volcanic center, covering an area of 28 squared kilometers. Now we come on to the last stage of activity, stage 4. This stage consists of the most recent activity, all sourced from fissures. The products young as you go anti-clockwise around the center of the region. In the east-northeast, you can see the pink lava flow. This is referred to as phase O and was a fissure eruption that occurred in 2008. When we put the chronology together, we can see how the spatial distribution has varied during the area's evolution. The figure here shows how the area covered by each lava flow was on average reduced over time. When we look at the fissures that opened in the north of the area, we can see that they're positioned directly around the Alu Dome. This is shown in figure A. The positions of the figures of stage 2 move progressively clockwise, whereas the fissures of stage 4, the recent activity, opened progressively anti-clockwise. When we combine this evidence with the curvilinear nature of the fissures and the perpendicular cones, which indicate radial fractures, we believe that this is indicating the presence of a cone sheet beneath the Alu Dome, as illustrated in figure B on this slide. This would align with the saucer-shaped sill argument proposed by McGee et al. 2017. Now we make our way further south towards the Borale volcanic complex. When looking at the positions of all the scoria cones to the west, we can see that these form a circular pattern around the area previously hypothesized to be a shield volcano. Alongside this, curvilinear faults within the volcanic center are observed. We therefore propose that these are a group of ring faults from the result of a collapse of a roof block of the shield volcano crater, alongside ring dikes which feed the volcanic cones. Further dating and fieldwork would need to be done to confirm both of these hypotheses, though. High proportion of lavas from Alu-Dalafilla and Borale are basaltic, with all samples in stages 1 and 2 being basaltic in composition. Stage 3, the volcanism sourced from the volcanic centres, shows a range of compositions, from basaltic trachyandesite all the way to rhyolite. This indicates that there may have been a period of low or even no activity, which would allow the magma to evolve through fractional crystallization, or the magmas may evolve through crustal assimilation. We also want to note that the magmas of stage 3 also had a much higher proportion of plagioclase feldspar compared to stages 1 and 2, but very little potassium feldspar. Stage 4, the recent fissures, were much more primitive in composition, similar to that observed in stages 1 and 2. To understand the evolution of the magmas, we modelled the geochemical variations using two approaches, a simple mass balance approach and using rhyolite melts. As you can see here, the more basic mass balance approach fitted much better. This showed a relatively simple mineral assemblage consisting of olivine, clinopyroxene, orthopyroxene, plagioclase feldspar and some oxide minerals. All compositions could be achieved through fractional crystallization alone, bar 4 samples. These 4 samples needed plagioclase assimilation, as shown in the aluminium-magnesium plot. When modelling with rhyolite melts, the conditions must be stated. We used 3 weight% of water and an oxygen fugacity of -4. We ran the model from 500 to 100 MPa and from 1300 to 800 degrees Celsius. Overall, we found a similar mineral assemblage to that of the other model, both matching what was observed. Overall, both models agree that compositions, bar those previously stated, can be achieved through fractional crystallization alone. However, further work would need to be done with trace elements to confirm for sure that there is minimal crustal influence. Finally, to summarize, there have been 4 main phases of activity at Alu-Dalafilla and Borale. 2 phases were basaltic fissure-dominated activity. This was followed by evolved activity from the volcanic centres themselves, and finally, recent activity has returned to basaltic fissure-source volcanism. Structures can be found within the region indicating the presence of ring dikes and cone sheets. And finally, almost all volcanic products can be produced through fractional crystallization alone. Thank you for listening, and I look forward to answering any questions.